Thanks everybody for coming today. I am going to talk about a programming language that we at COSADA are creating. So it's a brand new programming language. It's a little different from the programming languages you may have worked with before because this language is designed for artists. Artists today are working not just with paints and clay, they're working with all kinds of electronic media, so sounds and graphics, video, devices. So what we wanted to do with this programming language is provide a way for multimedia artists to combine different kinds of electronic media easily and be able to focus on the art that they're creating. So before we go any further, I'd like to give a little demo of our programming language. I'm going to make a hello world. What I'm going to do first is I'm dragging what we call nodes onto the canvas. Okay, so each node, for those of you familiar with programming, it's basically a function. So it has some input ports and it has some output ports, and it is in charge of doing something with the inputs and producing some outputs. Okay, so this display console window node is in charge of, well, displaying a console window, and it will pop up the text that I give it here. So I should do hello world. Oh, and I should zoom in so you can see it better. Okay, and this node here is in charge of sending an event to tell the display console window when to execute. Okay, so fire on start just sends one event when the composition first starts. So let's see what happens. Okay, so it just popped up a console window that displays hello world. Woo. Okay, well we can do something a little more exciting than this. So a lot of times we want things to happen more than once. So we want to do something repeatedly. So I'm going to replace the fire on start with a fire periodically, which is going to fire an event every 1 second. So we're going to repeatedly print out hello world. But here it goes, printing hello, 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 hello. Okay. And if I want to change what it's printing, I can just, hello, Wooster. Okay. So I can just change that while the program is running. So that's pretty handy, and we call that live coding, the ability to modify your composition while it's running. Okay, so that's our quick demo of some of the features we have so far in Vuo. I'm going to show more details about the language a little later. But what I want to do now is show another visual programming language that shows some of the things that we plan to implement in Vuo and we're working on right now, but we're not quite ready to demo them yet. This other environment is called Quartz Composer. And if you have a Mac, then you can get Quartz Composer for free. So what I'm going to do in Quartz Composer is I'm going to demonstrate building a multimedia composition. So I just dropped an image file onto the canvas, and what I want to do is display that image in the viewer here. You can do that pretty easily if I can spell correctly with a billboard. So all we have to do to make an image show up on the canvas is make this little connection here, and then it shows up. So this is another example of live coding, so we can see the composition being built up as I'm making it. For example, we'll make the image fill up the whole screen, and we can add some filters, be a little artistic with the image. So there's a whole list of nodes that you can work with for different kinds of media. So I'm going to add a distortion here. Just sneak it in the middle. Boom. Okay, so now it looks kind of weird. Okay, and now this is where it really gets interesting, because we can easily not just work with graphics, but also work with audio and just throw that right in. So I'm going to take this audio input node here, and so this is taking in audio from my microphone, and I can take the volume of that and hook it up to the bump distortion. So now when I talk, it makes this creepy child be creepy. Woo! Okay. Yep. So, yeah, so that's very creepy. Okay, so that is, that's Quartz Composer, and that demonstrates mixing together different kinds of media very easily, just with a drag and drop interface, and also being able to watch your composition being built without having to stop it and restart it every time you change it. So Quartz Composer and Vuo are both visual programming languages designed for multimedia artists, and these are not the only ones out there with the same intent. Several visual programming languages, well, lots of visual programming languages have been developed over the years, probably hundreds, and several of them have been specifically for multimedia artists. So what we're trying to do with Vuo is improve upon what these other visual programming languages have done and make it easier to use and make it higher performance. Okay, throughout this presentation, I want to show some videos of multimedia art because they're really cool, and also it gives you a better sense of what people might want to do with a system like Vuo. Okay, so this first video. Okay, so this was built partly with Quartz Composer, including a plugin that was developed by Quesada, and it was also developed using some projection mapping software called Mad Mapper, developed by Chin24 Architecture. So this is all live in person. This is not fancy video special effects. This is lighting projected onto that building. And it's interactive. Okay, so if you want to see more of that, then you can go check out the video. Yeah, that's one example of the kinds of things that people would want to use visual programming languages for. More about multimedia art and multimedia artists. So if you've been to an art gallery lately, or a science museum, or even some airports now, if you've been to a live music performance that has visuals going on in time with the music, then you've seen multimedia art. Okay, so the people who are creating this kind of multimedia art are the people that we want to support with Vuo. So how do we support them? Well, when we designed the Vuo programming language, we really had to think about the workflow of multimedia artists. Vuo is a programming language in a programming environment, like an IDE. The programming environments that you work with most of the time are probably going to be designed with certain tasks in mind. So they're designed for people with an engineering and mathematical background, people who have a certain kind of training in how to do programming, and people who are probably doing their work in a lab or in an office setting. Well, multimedia artists have very different needs than that. A lot of times they're doing their work in a noisy environment, so maybe right in the middle of a party or a music show, they're building some visuals, and they need something that they can work with without having to completely concentrate on it. They need something that's easy to learn, because if they have this great idea, or if a client comes to them with this great idea of some art to create, then they can't, take a year off and go learn how to program. They need to learn, just be able to pick up this environment and be able to start using it right away. And a lot of multimedia artists are coming at the idea of programming pretty differently from how we might learn it as computer scientists or mathematicians. So I have a picture of Bobby McFerrin up here. So he's a famous vocalist, Don't Worry, Be Happy. He's known for doing improvisation. And I heard an interview with him where he said that if he were going to teach a kid how to play the piano, then he wouldn't start with scales or like how to read notes off a page. He would start with improvisation right from the beginning. So he would say, here's one note. Learn how to play this one note, and then learn how to improvise on it. So do a bunch of different rhythms on this one note. And then once you've done that a bit, then here are some more notes you can play with. So maybe you can use your 5 fingers and improvise on those. Well, a lot of multimedia artists are kind of approaching programming that way as well. So not with a specific task in mind of, I need to display these certain things output on the screen, but with a more general approach of, hey, I want to sit down and just see what I can create with this environment. So with that in mind, we wanted to design the Vuo programming language to support that kind of workflow. So first of all, we wanted to make it a graphical language and with drag and drop elements, because we thought that would be much easier to work with than having to think about what to type. So with the drag and drop editor, you get a list of all the nodes that are available to you, so you can see right away what you can do and just sort of brainstorm about what you can make. And with the editor, it also prevents you from doing anything you're not allowed to do. So there's no, there are no syntax errors. You can't, get your semicolon in the wrong place or something, or because the editor is making sure that you're only doing things with nodes and cables that you're allowed to do. We wanted to make a very high-level language. So you guys know the difference between high-level and low-level languages? So high-level, well, low-level is down at the level of the computer. Like assembly code, machine code, and then as we get to higher and higher levels, we get closer to the way that humans think. So in terms of sentences or in terms of diagrams, or, yeah, so higher level. So we wanted to have this high-level language that allows the user to create a composition that does very complex things, but doesn't make the user think about things like memory management or multi-threading or anything like that. It handles all of that for the user. We also wanted to make a minimal language. So when you drag things onto the canvas, there are only a few things you can drag around, nodes and cables basically. There's not a bunch of other stuff that you can drag around that you have to figure out what it does and how it can all interact. And finally, of course, we wanted to support live coding because that's the best way to allow multimedia artists to improvise. So, as I said, we wanted to create Vuo to build on the strengths of some of the existing visual programming languages and also try to improve upon where they're weak. So a couple of things that we wanted to improve on with Vuo. We wanted to improve on usability. So although there haven't been any scientific usability studies that we know of these visual programming languages up here, from our experience and from the experience of artists that we've talked to, Quartz Composer is much easier to use than Max, Pure Data, or FearFoul. So we wanted to continue that trend with Vuo and make it, well, even easier to use. We also wanted to improve upon the performance. Specifically here, we wanted to make compositions automatically compiled and multi-threaded. So that way they're compiled instead of being interpreted, which allows them to run faster, and they're automatically multi-threaded, which allows them to take better advantage of multiple CPUs on your machine. And one thing that we don't have yet in Vuo is distributed computing, but that's something we have planned for the future. Finally, we wanted to make Vuo open source, but we also wanted to make sure that it could pay for itself and continue to support its own development. So what we ended up with was a subscription model where if you pay for a subscription, then you get the latest, greatest version, including the source code. And if you don't want to pay for it, you want to get the free version, then you get the 1-year-old source code. So in either case, it's open source. So now I have a couple more examples of multimedia art to show. So the first one, this is music by a guy called Llvm. And the visuals that show up behind him are being created live. So this is a Quartz Composer composition that's being added to as the music is playing.
So is he on a computer? Is somebody on a computer doing that?
Yeah, there's somebody sitting like right here.
Okay.
that you can't see. Okay. So that's an example of improvisation. And then I have another one I want to show here. 3D models being projected on giant semi-transparent screens in a church. And that one was by Vibeke Bertelsen. Now I want to get more into the technical elements of the Vuo programming language and the Vuo compiler. So I'm going to go through a few examples to illustrate the rules that the Vuo programming language is based on. So this is just hello world again. So just to review, in Vuo, everything is based around events. So events are what make things happen in Vuo. So this thing here is a trigger port that can fire an event. The event travels through a cable, and whenever an event hits this display console window node, then this node executes. So this is an example that has two event sources going on at the same time. So each of these nodes here is going to fire an event every 1 second. There's no guarantee about which one is going to fire first, so they're completely independent of each other. And they could fire at pretty much the same time. So we have events firing counts. This one is counting up. this one is counting down, and then it's displaying in the console window. Yeah, so what I wanted to illustrate with that, there's some basic protection against race conditions in Vuo. So what happens if this one fires an event and this one fires an event right after it? So maybe this event goes here, 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 and then this event fires. Well, in Vuo, this event can't come through and overtake the other one, because that could mess up the data that's in here and end up printing the wrong thing. Instead, this one is supposed to wait. So we have some basic protection against race conditions, and there's thread synchronization built into the language. So it's happening even though the user doesn't necessarily know what thread synchronization is. Okay, let me show another example. So what this composition is going to do is it's going to fire an event which is going to travel through this composition to the downstream nodes. And what's going to happen here, when it gets out of the count node, this event is going to split off. So we can kind of see, just by looking, thinking of this as a diagram, we can see that it's okay for divide and add to execute at the same time because there's no way they can affect each other. So the Vuo compiler is actually going to allow these to be multi-threaded so they can execute concurrently. And then there's some thread synchronization happening because this event is going to split up here and then it's going to join back up here. So select input is going to wait until divide and add have finished executing before select input is ready to execute. So what this is doing is select input, this is doing a little control flow. So it's picking, so we're checking here if the count is odd or even. And if it's even, it's just going to pass the count right through to the console window here. And if it's odd, then it's going to add 1 and then pass that through. That was an example of another kind of thread synchronization. And I have one more example I want to show. This is an example of a feedback loop. Okay, so this is another kind of control structure in Vuo. This feedback loop is actually, you saw the count node before. What this composition is doing is redundant to the count node. So this one is also just going to count up. So it's just counting up by ones. But what's special about this one is that the way the event flows through the composition, so it's going to come out of the fired port, it's going to go into this hold value node. This hold value node, the first time it executes, it's going to take, well, yeah, you could read it in the documentation if you didn't have me explaining it, but it's going to take the initial value here the first time it executes, and then after that initial value gets sent through the composition and updated, from then on it's going to take the updated value. So it allows you to accumulate a value. And this is an interesting control flow because the event is going to travel to hold and then onto the add node where it's going to add 1, and then it comes back to hold. And the event is going to stop here because we don't want to allow users to accidentally create infinite feedback loops, because that would be annoying if you didn't even know what an infinite loop was. Why is this not working? Okay, so instead what we do is whenever there's a feedback loop, we require that the event run into one of these blocker ports. So you may have noticed that some nodes have these little eyebrows over ports. So these block events, and that means that the event, once it hits here, it's not going to come back through. So these blockers allow a little bit of control flow with how events flow through the graph. Okay, so just to sum up what we talked about, so events are what make things happen in Vuo, and events and the data can flow through cables. We have some thread synchronization, so events can't kind of overlap and outrace each other. They have to wait. Events can split up and nodes can execute concurrently, and then events can get back together, and there's thread synchronization to make sure that that happens as you would expect. We have some control flow for events based on when they run into the blocker input ports. We have some rules about feedback loops to make sure that you don't accidentally create an infinite loop. Okay, so now that you know the simple rules of Vuo, it's time to write the compiler. Okay, so problem. How do we take a composition, a graphical representation of something, and turn it into code that is at the level of the machine? So we have to figure out how to schedule nodes to execute at the correct time. Okay, so this is our compiler. And just looking at this in a little more detail, so we need to take the composition, which if you open it up in a text editor, it's just going to be a list of all the nodes and cables. And we need to turn that into an executable or dynamic library. So this is our machine code specific to some architecture. So the way that we do that is we take the composition and we generate some code for it. And we also we generate some code that schedules the different nodes to execute at the proper time. And we also have separately some code that says what each node is supposed to do. So, for example, the source code for the display console window node is going to be like text code that pops up a console window and adds text to it at the appropriate time. Okay, so we take the composition and all of these supporting files and we turn them into an intermediate representation called Llvm bitcode. Okay, has anybody heard of Llvm before? Ooh, yeah. Okay, so Llvm, the Llvm compiler infrastructure is an open source project that is extremely handy if you're writing a compiler or doing anything with, or doing some things with language translation. So it provides an API where you can, or a set of functions that you can use to generate code. So if I call the correct functions, then I can generate a set of instructions in Llvm bitcode, which looks kind of like assembly code, but it's at a slightly higher level. So then Llvm also is able to take this intermediate representation of bitcode and compile it down to machine code specific to various architectures. So that's real handy because we don't have to worry about translating directly to like the x86-64 architecture, which is hard. We can just translate to one intermediate representation and Llvm does the rest. Now I want to drill down a little bit into this diagram and talk about the process of going from the composition to the Llvm bitcode. The problem is, how do we generate code that schedules nodes to execute at the time that we want them to? Okay, so we're writing a compiler that takes a composition like this and turns it into a set of instructions that the computer can execute. Well, let's look at a simpler problem, which is just what is the code we want to generate? Okay, so if we were to write a C or Java or whatever language program that is equivalent to this composition, what would it look like? There are probably lots of different ways to do it, but here's how we did it. We have an event handler that executes whenever the trigger port fires an event. So we have one of these for each trigger port. And what that event handler is going to do is it's going to schedule each of the nodes that are downstream of it to execute. Okay, but before it causes them to execute, the first thing it needs to do is claim some semaphores. So we're using, or think of semaphores just as locks in this case. So each node has a lock associated with it, and you can lock and unlock a node, and that allows us to do some thread synchronization so that events aren't all on top of each other. They have to wait their turn to go through the composition. Okay, so we do our thread synchronization with semaphores, and then we transmit an event along the first cable. So how could we represent transmitting an event if we were going to write this as a program in C, Java, C++, whatever you guys use? We have a variable that for each input port, so like there's a variable for the increment input port of the count node that it's just a Boolean, and it stores whether the input port received an event recently. And while we're at it, we can also have another variable for each input port that stores the data that's currently in that input port. Okay, so that's just how we express these data and events, is just with variables. Okay, so the rest of what we need to do is schedule all the downstream nodes to execute. So let's drill down into that. What does it look like to schedule each one of these to execute? Ignore this thing about the dispatch group for a minute. I'll talk about it when we get to the next node. So if we want the count node to execute, what we need to do is have the count node do its job, which is increment, well, yeah, in this case, since we have a cable coming into increment, it's going to increment the current count and calculate the new count, output that. Okay, so we're going to have a function that's associated with each node. So the count node's function is going to count up. The divide node's function is going to take two numbers, divide them, and give you the quotient and remainder, etc. Okay, so we need to call that function, and then we need to transmit the data along each of the output cables coming out of that node. Okay, so again, we're just copying the data into the variable associated with each input port. You need to signal the semaphore for the count node to say that we're done using it for this event, so that the next event that comes along can use this node. So the next node that needs to execute is either going to be add or divide, so they can both execute concurrently. So the way that we accomplish this is with something called dispatch groups. Have any of you worked with libdispatch before, Grand Central Dispatch? It's really, really cool. It's a multi-threading library that works, it's kind of a level up above threads and locks, and it has abstractions that are, at least for me, closer to the way that I think about threading. So a dispatch group is one of those abstractions, and it allows you to submit tasks to a dispatch group, and you can have another dispatch group that waits on all the tasks to complete in the first dispatch group. So we're using that here to make sure that the add and the divide nodes wait on the count node before they execute, but they don't have to wait on each other. Okay, so add is going to wait on the dispatch group for count before it executes, and then we just do the same thing before for count. So we call, or like we did for count, so we call the function for add, which is going to add the two inputs, and then we copy the output over to the next node through the cable, and we signal the semaphore. Okay, so same idea for divide. Okay, so I'm going to wait on the dispatch group to make sure that divide executes after count, and then do the division and send the data along on the output cable. Okay, and then these last three nodes, since they're all in a straight line, we don't have to do anything fancy with dispatch groups between those three, because we know they're all always going to execute in sequence. So select input needs to wait on all of its input cables to send data before it can begin executing. So again, it's using dispatch groups to do that. And then we're going to do the same thing as before with executing each node, sending the data on, and unlocking the node. Okay, so this is what the generated code looks like. So if you were to create this composition in Vuo and you were to hit the run button, then it would generate this code. This is the compiled composition. Okay. Now, if we take a step back, how do we generate this code? What is the algorithm for the compiler? Well, it's pretty similar to what I just talked about, except everything is a step back. So instead of doing things directly, we're generating code to do things. So generate code to wait on semaphores, generate code to transmit data along the cables, etc. Okay, and since it's handling since it needs to handle all types of compositions instead of just that one composition, then we need to handle special cases. For example, there are some cases where an event might get blocked partway through the composition. So we need to check that, check and make sure that a node actually received an event before we actually execute it. So it's a little more general case. But yeah, so that's a parallelizing compiler. Some libraries we used that might be useful to you as students or faculty. One was GraphViz, so that's what we use for storing the composition in a text format and parsing it. It's also useful for drawing graphs with nodes and edges. We use libdispatch, which I mentioned for multi-threading, and we used Llvm for generating code. And in case you're wondering, this is some sample code for Llvm. So what it looks like to generate a simple function call. So if we want to generate a call to the Sterling function in C, this is what it would look like. So we have Llvm provides data types that represent elements in your program. So there's a function data type, there are type data types, function type data types, and instruction data types for the code that you generate. So it's kind of confusing writing code about code, but it's also pretty handy. Much better than having to like generate text code in C or something. Okay, so just to summarize what I talked about so far, and then I'll show another video, and then say a few more words, and then I'll be done. So we got kind of deep into the Vuo compiler, talking about the algorithm for generating code to schedule nodes in a composition. How we got onto that was we were talking about using a parallelizing compiler so that Vuo has high performance, allowing nodes to execute concurrently when possible. And the reason we're doing that is we want to provide a very high-level language for multimedia artists to use so that they can have a powerful tool, be able to create compositions that can work with large amounts of data, but still not have to be expert programmers. And all of that, what it really comes down to is supporting creativity. So providing a tool for artists to do what they really want to do without having to think about the tool, they can focus on the task. One last multimedia art. Okay, so Cosada was a little bit involved in this one too.
Two tall Swatch bars are attached to my...
This one was created by a guy named Gabe Mott. It's called Colorbox. And Cosada helped out a little bit with the gesture recognition. So we have, or he has a Connect set up there, and then he's using gestures to control what's going on the screens.
The flat gray circle is 50% gray. My right hand can touch a square and it'll change the color of the room.
Okay, so you can check out more of that video later if you want. But it was an experiment in, or exploration of colors. Yeah, Vuo is being developed by Cosada. This is us, the company that I work for, and we're small company based in Athens, Ohio. Yeah, if you found this presentation interesting, then we hope that you'll want to get involved in visual programming languages. You can use them directly. we want to provide a place with the Vuo website where people can share nodes and compositions, and we even plan to provide a store where people can sell them. If you're more into research, there's a lot of research that could be done with visual programming languages. So I mentioned usability studies. So comparing the usability of different visual programming languages, performance benchmarks to compare their performance, and just lots of different ways that you could use or do research or use visual programming to present your research. And also I think they'd be a good teaching tool, whether you're trying to teach intro programming to computer science students or just to anybody. So if you want to find out where Vuo is headed, you can go to the website vuo.org and check out our roadmap. And if you're interested in becoming more involved, then please talk to us at lunch. So Vuo is designed to support the creative flow of multimedia artists. And thank you from everybody at COSADA for listening.
Does anyone have any questions?
Can you explain live code and compilation of compositions and how that works? Because that's just kind of going.
Yeah, that's been one of the biggest challenges. So if we were running the composition in an interpreter, then it would not be so hard to update it as it's running. But what we're actually doing is we compile the composition to a dynamic library, and then we swap it out as the composition gets updated if we're making major updates to the composition, like changing the nodes around or something. And
So is there a link from the original kind of structure of the program, or maybe the bit code, to that library so you know where everything is located and you can do the swap? Does that make sense? Does my question make any sense? I'm trying to figure out how you recognize which sections of the code that you're going to actually be changing.
Oh, yeah. We maintain a data structure of the nodes and cables in the composition. So if you say you add a node and you rebuild the composition, then the nodes that you already have are going to stay the same. Does that answer your question?
Yeah.
Okay. And we also have some communication set up between the Vuo editor and the running composition, so that if you just do a minor change, like changing hello world to hello Wooster, then it just sends a message to the composition. You don't have to rebuild it. Yes?
How does one go about making a new node? Say an artist has a really good idea, but it's not quite covered in any of the nodes that are already with it. Do they have to pay somebody or get somebody to program it for them, or is there a way for them to do it themselves?
Oh, that is such a good question. So, thank you. Right now, all of the nodes are implemented in C. So if you want to create a new node, then you write up a C file that has a few certain functions that you have to implement. But in a few months, we're going to be working on being able to turn a composition into a node. So, yeah, being able to, well, basically build things up to higher and higher levels of abstraction.
Okay.
Any other questions? Okay, let's thank the speaker again. And lunch in Lowry if you'd like to join us.